Okay, thanks. So it's always wonderful to be at these It from Qubit shindigs. A few of you already heard a version of this talk at the Simons meeting in New York, but even for those who have, there will be some new twists in the story, so hopefully you won't leave demanding a refund or whatever. For everyone, everything I'm going to say in this talk is totally, mathematically elementary and simple. So let me, let no one pretend otherwise. But there are, as I said, there are twists in the story that were, surprising and unexpected to me. So maybe to some of you as well. So as with so many other things in this subject, this talk starts with a question that Lenny asked. So he was interested in this question about state dependence of observables. Okay, so what does that mean? And I'm basically just a computer science consultant in this field, right? So I get a consulting assignment. I don't understand exactly where it came from, but I can try to give you the Scientific American version of it. Right? So in discussions about firewalls, for example. So if you want to know which bulk of operators an observer, Alice, say, is allowed to apply, well, that's going to depend in general, on the space-time background, in our usual way of thinking about it. Like, is there a black hole there, or is there not one? Right, that's what sort of will determine the algebra of observables. Okay, the trouble is that in these same discussions, we would also like to treat the space-time background as a quantum state itself, for example, in the context of ADS-CFT. Okay, so then combining these things, we would reach the conclusion that which operators Alice can apply depends on the quantum state. But that just doesn't make any sense in terms of standard quantum mechanics. That's just nonsense.
If you knew about the gauge invariance, then you wouldn't say that.
All right, well, I don't, so therefore I do say it. Okay, so what Lenny wanted to say about this, and what I think is sort of the natural thing that I would have guessed about it also, is that in some sense this is really another instance of the Everettian many worlds perspective of quantum mechanics. In action. So, in other words, there's some object that, from a godlike perspective, one could regard as just a single pure state, like that. But which is actually a superposition of two branches that are so macroscopically distinct that, in practice, we would never observe interference between them. One representing one space-time background, the other representing the other, right? And therefore, in practice, we can treat these as two different space-time backgrounds with different sets of observables. Okay, but then, the question became, well, sort of, what are the conditions for this to happen? For sort of, a branching to happen between, two backgrounds or two macroscopically, distinct configurations that are going to be so different from each other that, yes, we are really confident that we can neglect the interference between them from this point forward, right? And of course, that's a general, interesting question about quantum mechanics, even aside from the applications to quantum gravity, right? It's a question that lots of people in quantum foundations have thought about. Wojciech, Jess, just here in the audience have written many things about these questions. Okay, but now the way that Lenny wanted to study this question was by introducing a particular kind of distance metric on quantum pure states, which he calls relative state complexity. Okay, so given two pure states, V and W, let's say that there are n qubits for simplicity, we can define the relative state complexity, say C of V going to W, as the number of gates in the smallest quantum circuit that would take V as input and output W. Okay. So there's a few things that we need to clarify about this definition. First of all, which gates do we mean? Well, let's say Hadamard and Toffoli gates. We fix some particular set of one and gates acting on a small number of qubits. Okay, now, do we have to exactly produce W, or is it enough to merely approximately produce it? That's a technical issue that will often come up. I'll say, what we really mean is like C sub epsilon, meaning that, we're interested in the size of the smallest quantum circuit that outputs an epsilon approximation to W. Where I'll think of epsilon as typically being exponentially small, and I will suppress the dependence on epsilon unless it becomes important. Okay, so and then one issue which is important is the use of ancillas. Okay, so are we allowed to use ancilla qubits? In doing this transformation? What I'll say is that you're allowed to use ancillas that are initialized, say, to the 0 state, as long as you return them to the 0 state by the end. Okay, if you don't return them to the 0 state, then you actually get a different notion, which will not work for everything that I need. Okay, so let's see. So what can we say about this metric? First of all, is it a metric? Well, yeah, it's symmetric. Which is quite easy to see. Unitary circuits are reversible. It satisfies the triangle inequality, at least if we allow some wiggle room that this epsilon can become a 2 epsilon. Okay, and for every pair of n qubit states, this complexity will range. Basically, between like 0 and 2 to the n, with, it'll be 0 if and only if, the states are equal or nearly equal. And for a sort of generic or random pair of 2 qubit states, it's easy to see by a counting argument that this relative complexity will almost always be 2 to the n, or close to 2 to the n. Okay. So importantly, V and W could be orthogonal, in Hilbert space, but nevertheless extremely close in this distance metric, right? Like differing only by flipping 1 qubit or something. Okay. Conversely, V and W could also be very, very close in Hilbert space, like differing by 1/10 or something. Okay, but as long as epsilon is less than 1/10, this relative complexity could be exponentially large. Okay, so this is very, very different than any ordinary Hilbert space inner product or anything like that. Okay, so now Lenny's conjecture was that this relative complexity should, in some sense, precisely characterize when it is feasible to observe macroscopic coherence between V and W. Okay, so that is, his conjecture was that it should be possible, say, to distinguish V plus W from V minus W, or to distinguish either of them from the incoherent mixture, VV plus WW, if and only if this relative complexity is small. Right? What do we mean small? Well, a theoretical computer scientist would probably want to say polynomially bounded. A physicist might impose something more stringent than that. Small enough that you can do it in the lifetime of the universe or whatever. Okay. But then so is that actually a theorem? Well, Lenny said a theorem. What's that? so that was my consulting assignment. To say, is this true, and in what sense is it true? All right. So indeed, this is very close to true. So I'll prove a related statement, but with a few interesting twists. Okay. So all right. So first of all, let me assume throughout that V and W are orthogonal states. Okay, this will be important. I mean, you know, one can generalize the story to when V and W are not orthogonal, but let me assume in this talk that they are. Okay, and then I'll call this superposition psi, this V plus W, and this V minus W, I'll call it phi. Okay, and now so relative state complexity was defined just in terms of a unitary that maps V to W, right? So you know, we looked at the circuit complexity, the minimum circuit complexity of a unitary U such that UV equals W. Okay, and of course, if we had such a circuit, then we would also have a circuit, you know, to map W to V, namely whichever one implements U dagger. Okay, but then we could also ask for something stronger, which is we could ask for the same unitary U mapping V to W and also W to V. Okay, I'll call that a swap operation. Okay, so now I claim that having this kind of swap operation is precisely equivalent to being able to perfectly distinguish this superposition from this one. Okay, where it's important that this swap is exactly as I wrote it, with no phases here. We'll come back to that. Okay. Okay. So why is that? Well, this is like freshman quantum computing. Okay, but I can, which it now is like I'm teaching it to some freshmen actually right now, but I could literally put it as a homework in my course. Okay, but let me just to go through it. So suppose that we had such a U. How do we use it to distinguish these two superpositions? Well, I do it by I prepare a control qubit in the plus state. This 0 plus 1 over root 2, and then over here I have, say, either psi or phi, and then conditioned on this control qubit being 1, I apply U over here, and then I measure this control qubit in the 0 plus 1 and 0 minus 1 basis. Okay, and if I had psi, then my applying U did nothing, right? So I always get plus over here. And if I had phi over here, then my applying U threw in a negative 1 phase. Okay, so then I would get 0 minus 1 on the control qubit. Okay, good. How about the opposite direction? Suppose that I had a unitary transformation A with the property that A applied to psi gives me 0, tensor some other garbage, and A applied to phi gives me 1, tensor some other garbage. Okay, so in other words, this is an operation that perfectly distinguishes psi from phi, that tells me the relative phase here. Okay, then that's merely solving a yes or no decision problem. So a priori it might seem surprising that such an operation would necessarily be usable to actually implement the physical transformation that you want. Okay, but it is usable for that, and all you have to do is okay. So let's notice that V is psi plus phi. And W is psi minus phi. Okay? And our goal is to swap these two states. Okay, so how do we do that? Well, now it's pretty plain to see. We apply A, and then we apply A to this thing or to this thing, and then we look conditioned on the control qubit being 1. We apply a minus 1. And then we apply a dagger, right? So when we said and we had an operation, the operation could have included measurements, okay? But by the church of the larger Hilbert space, you can always think of an operation that includes a measurement as just a unitary transformation on some larger space. So I'm using that fact here, right? I'm using the fact that, you know, we could have a unitary A, and after we apply A, we could do A, and then a phase operation, and then a dagger. Okay, and that will replace this plus by a minus and the minus by a plus. Okay.
If A is a measurement, can't that just be really hard if you can't do a dagger in practice? Isn't that sort of what we're trying to get at?
Yes, right. So all I'm saying here is that if I had a small circuit to implement A, you know, assuming I did, then I would necessarily also have a small circuit to, you know, interchange these two states. Right, and in fact, you know, the circuit complexities of the two tasks are linearly related to one another. You know, related to one another by basically a factor of 2. Okay, that's what I'm saying. You know, and of course, you know, if A, you know, and then the converse of that is that, well, if A is hard, well, then interchanging these two also has to be hard. Okay, so. Okay, but then, you know, we could say, okay, but I changed the question, right? Because, you know, maybe we have a U that maps V to W, but it doesn't simultaneously map W to V. You know, so what then? Okay, but in fact, you know, it's useful to think of that case as simply one instance of a more general situation. Okay, which is, you know, I may, you know, be doing this task or this task less than perfectly. Okay, so you know, by less than perfectly could mean very less than perfectly, right? Like I do this, but I don't do this at all, for example. Okay, and so now, you know, let's just ask the general question. You know, how well does an imperfect ability to do this task imply an imperfect ability to do this task, and vice versa? Okay, so now let me state a theorem. One of these things with that'll have a box. Okay, so what it says is, okay, so as usual, you know, I'll let V and W be orthogonal. Okay, orthogonal and qubit states. And now I'm going to suppose that we have available a unitary transformation U such that WUV has some value, A, and VUW has some other value, B. Okay? And now I'm interested in using such a U, how well could I distinguish V plus W from V minus W? Okay? And the result will be that I can distinguish psi, V plus W, from phi, which is V minus W, with bias. You know, in computer science, bias just means like the probability that I accept this guy minus the probability that I accept that guy. Okay? The bias will just be absolute value of A plus B over 2. Simple expression. Okay? So, does anyone want me to prove this? Yes. All right. The proof is another homework exercise, basically.
What's that U meaning here?
Okay. So let me give a more careful statement. Okay. So the claim is, you know, suppose that the circuit, you know, there is a U of circuit complexity, you know, at most T, that does this, you know, that has this behavior. Then I claim that there is a circuit of complexity L of T, you know, like 2T or 3T or something, that distinguishes psi from phi with this bias.
So you're thinking of A and B as small numbers. So.
They might be. I mean, you know, I'll go into, you know, the different possibilities for A and B and what it would mean for this. Okay, you know, they could really be anything. Okay, so basically to prove it, I use exactly the same procedure from before, the one involving the control qubit that's in the plus state, and then I measure to see if it's in plus or minus, and I just do a calculation of what's the success probability, and then, okay, there is an interesting twist. When I do the calculation, the answer that I get at the end is actually the real part of A plus B divided by 2, okay? But, so then, like, if A was I and B was, if A and B were both I, then this would be 0, okay? But then I noticed, well, wait a minute, if A and B were both I, then I could just multiply U by a global, minus I, and then this would be 1. All right, so I say, if I want to optimize the expression, then I'll always multiply U by a scalar in order to make this thing real, okay? And if I do that, then I get this.
While you're talking about phases, A
Yes.
and B could cancel each other, right? You have
Yes, indeed they could. And this is my first surprising twist in the story. Okay, that I worked this out, and I was basically okay, fine. They can distinguish. You can then distinguish psi from phi. And I wasn't even thinking about the case. Well, what if A is 1 and B is -1, right? And in that particular case, I do not have an equivalence. Okay, in the case that A is 1 and B is -1, in that one case, okay, I would have like a swapping ability. Namely, I would have the ability to map V to W, and the ability to map, and at the same time to map W to -V. Right? I would have this, and yet this would imply no distinguishing ability, none whatsoever. Okay, the bias is 0. Okay, in every other case, I can let this be any phase, relative to this one, other than -1, and then I will get some distinguishing ability over here. But if this is exactly -1, then I get none. Okay, yes.
Sorry, but if I consider spin on top just a qubit,
Yeah.
then the spin rotation has this property. Like if I rotate by pi, then
Yeah. So okay. So let me just ask a general question now. Which is an open question as far as I know, right? Which is there any situation where I have two pure states V and W, and I have an efficient circuit that maps V to W and W to -V, but I have no efficient circuit that swaps them without a phase, right? I don't in other words, this is a theoretical problem that I don't know if there's any situation in circuit complexity where this ever becomes an actual problem, right? I would love to know the answer to that question, okay? I think, like the math must be telling us something here, and I don't know what. Okay?
Do you know of an example in which you have UV equals W, and you don't know how to convert it to UW?
Yeah, oh yeah, and you don't know how to get both. Oh yeah, I was going to talk about that later, but I can tell you right now, I do have such an example. Let me just flip to it later. Yes, good. Let me give you an example right now. Here's my example.
Yeah, people in the back probably can't.
Oh, I'm sorry. Okay, so. All right. Well, my first example is just let V be the all zero state, let W be the all zero state acted on by some crazy random circuit. Okay. I would have no idea in general how to plot, right?
Right, but it's an explicit example.
Yeah. Okay. So let me give you an explicit example. Well, are Haar random states explicit?
Not very.
Well, all right, but okay. The advantage of this example, Dorit, is that I think that a separation would actually be provable, unconditionally provable in this case. Okay. So here's my example. Let V be 1/√3, 0, A to 0, 1, A to 1, 2, A to 2. While W is 1/√3, 1, A to 0, 2 eta 1 plus 0 eta 2. Okay, where eta 0, eta 1, and eta 2 are just 3 uniform, independent n-qubit Haar random states. Okay, well then it's
Orthogonal
point.
or not?
What?
Are they assumed to be orthogonal?
No, they're just they don't have to be. They're just all Haar random. So in practice, they will be near
But also
near-
are random relative to each other?
That's right, that's right. Yeah, so in practice, they're very close to orthogonal. But yeah, I don't agree with that. Okay, so then it's quite easy to build a unitary that would map V to W. Namely, I just increment this Q trig by 1, right? Likewise to map W to V. Okay, but how do I swap them? Okay, so I haven't actually written out a proof yet, but I believe that it should be provable that with overwhelming probability over the choice of the etas, that swapping V and W would require, with perfect fidelity, would require an exponentially large circuit. This is my conjecture. Yes.
But in some sense, with regards to how we want to apply it sort of in physics and
Yeah.
you being somehow a time evolution,
Yeah.
wouldn't this be the generic case that you don't swap the time you want
Yes. Yes, yeah, that's basically what I was saying up here. Yes, you're right. Okay, so, but now to take another case of this theory, so the case A is 1 and B is -1 was, extremely interesting to me here, because here you have, there you have swappability without distinguishability. Okay, but we could also consider the case A is 1 and B is 0, right? And this is the case where basically I have a unitary that maps V to W, but it maps W to something that is orthogonal to both V and W, right? So it just, in other words, basically, it just maps V to W and W to something else. Okay, and in that case, we see that mappability does imply distinguishability, namely distinguishability with a bias of 1/2. Okay, so not perfect distinguishability, but but pretty good. Okay, like 3/4 versus 1/4 probabilities. Okay, so what else? Okay, so let me. Then move on to theorem 2. Okay, so again, now I'll let psi and phi be two orthogonal states. And we'll suppose that we have a procedure A that accepts psi with probability 1 minus epsilon, and it accepts phi with probability delta. Okay, so imagine, accept psi, imagine with probability pretty close to 1, and accept phi with probability pretty close to 0. Okay, then, using A, or, with a circuit which is, only very slightly larger than our circuit for A, we can map V, which is psi plus phi, to W equals psi minus phi, and in fact swap them. Right, swap with a fidelity of 1 minus epsilon minus delta. Okay, so this is actually a tight converse to theorem 1. This if you look at what it means, right? And it's a very simple expression. Okay, so like so basically, if epsilon and delta are both 0, then this reduces to the observation that I showed you before, right? If epsilon and delta are both 1/2, well then this is just saying that, well, if I have no distinguishing ability, then that doesn't imply any swapping ability. Yes?
Is A a projection operator?
Good. So A, so once again, as in the earlier example, right? Like I'll imagine that, that like in general, my procedure for A could involve a projection operator. But if I had a circuit to do it, then I could also just omit the projection operator, treat it as a unitary transformation, right? And then, apply the inverse of that unitary transformation. Okay, so this is, and then indeed, that's exactly what's done in the proof of this theorem. Okay, so, what I do, to prove this, again, it's just the same procedure that I showed you before in the perfect case, right? That I would just take the circuit, that implements A, everything in the circuit except for the final measurement of a qubit to see if it's 0 or 1, right? I apply that circuit, then I do a conditional phase, and then finally I apply the inverse of the circuit, okay? And then I calculate with what probability, with what fidelity will that map V to W and vice versa. And when you calculate it, you get this number. Okay? And and here you don't have the, because these are measurements and they just, either succeed or fail at this distinguishing task. There's no issue of phases canceling in this converse theorem.
Are ancillaries involved?
What?
Are ancillaries
Oh yeah. A is allowed to use ancillaries, certainly. Yes. Yeah.
And you still want to return them to back where they were beforehand?
Yes. Yes.
Exactly. Not epsilon delta.
Well, I mean, as long as I'm discussing C sub epsilon, then we'll say, you only have to, return them to epsilon close to where they were beforehand, right? But but I'll imagine epsilon as being very, very small. Okay. Okay. So all right. So let me. Yeah.
So you're basically equating these two. Do you actually say that distinguishing implies?
Well, yeah. Like in the sense of these two theorems, we could say swapping, a swapping V with W is equivalent to distinguishing V plus W from V minus W.
No, but
and approximately what?
I'm asking if distinguishing for you implies distinguishing with close to 1 probability.
Oh, well, these theorems are true for the full range of epsilon and delta. So even if epsilon and delta are both very close to a half, if they're both 0.499, right, this will still give you, a mapping that has some non-zero fidelity.
Yeah, I was basically asking if you can amplify.
Oh, well, okay, but see, these are not, like mapping V to W is not a decision problem, right? So I don't know how to do amplification in general for that kind of problem, right? You may be able to just do it with some fidelity, and then no matter how much resources you expend short of exponential, you may not be able to do it with better fidelity. Okay, so let me make just a few more remarks about this. Okay, so certainly, the ability to swap V and W is not equivalent to the ability to distinguish V and W themselves. Okay, it's only equivalent to the ability to distinguish V plus W from V minus W. Okay, and it's very easy to see examples of this. So, all right, let me erase theorem 1. Okay, so here's an example. Let's let V be the all zero state. And let's let W be some arbitrary superposition over n-bit strings, some like complicated, some exponentially complicated state which happens to be orthogonal to the all zero state. Okay? Then, it is trivial to distinguish V from W by a small circuit, right? Just check if it's, if you have all zeros or not. Okay, but mapping V to W, or for that matter, mapping W to V, will in general be exponentially hard, right? Just by a counting argument. Yes.
I guess that's a good trivial question.
Yeah.
So roughly speaking, there's the operator that swaps the two.
Yes.
And then we can imagine some sort of canonical conjugate which acts as 1 on one of them and minus 1 on the other one.
Yeah.
So if we also had that operator, then wouldn't they everything would be easy?
I think so, yeah, I think that's
So
right.
can we formulate things as somehow we're interested in a situation where somehow the poly X operator is simple and the poly Z operator is complicated, or we're trying to...
I think so. That might be related to what I'm about to say next. Okay. Yeah, like you do have these situations, right? Like the situation that I'm discussing, can arise whenever we have two complementary bases.
Yeah,
right?
yeah.
And yeah. That's right. So this is okay. So let me show it in this example, and I'll see if that addresses what you're asking about. Okay. So So in this case, distinguishing V from W is trivial. Mapping V to W is hard. Conversely, we could consider V plus W and V minus W. These two states. And now these are states where it is trivial to map this to this. In fact, it's trivial to swap the two. And yet distinguishing these two is exponentially hard. How do we know that it's exponentially hard? Well, because it's equivalent to mapping this to this, which we already said is exponentially hard by a counting argument. Okay, so the general rule is that ease of swapping in one basis implies ease of distinguishing in the conjugate basis, and vice versa. Okay, and I should say that I phrased it in terms of the 0, 1, and plus minus bases, but this would actually hold for any pair of conjugate bases. Okay, so it would also hold if I used the 0, 1 basis and the 0 plus I1 and 0 minus I1 bases. Right? Again. Ease of swapping in the one basis would imply ease of distinguishing in the other basis, and vice versa. Okay. So, let's see. Okay, so now my second remark. Why was it important in our definition of relative complexity that all the ancilla qubits were returned to the 0 state by the end? Well, it was important precisely because, when I gave that construction to prove the equivalence theorem, I had to apply this, unitary A, that's, every, the whole measurement operator except for the measurement part of it, right? And then I also had to apply A dagger, okay? And if A were to, let's say, map V to W, but then, also leave some do the distinguishing task, but then also leave some ancilla around at the end, well then, because of that ancilla, I wouldn't be able to apply A dagger. Okay, and so this is why it was important that when I defined the relative complexity of mapping V to W, I have to consider circuits that just take V and produce exactly W and not W tensor garbage. Okay, but this actually relates to one of my favorite open questions about the circuit complexity of quantum states, which I can't resist mentioning. Okay, and the problem is simply, is there, say, an n-qubit state psi such that the circuit complexity of psi tensor some garbage is small? So in other words, there is some garbage state such that it is easy to prepare, starting from the all zero state, psi tensor some other garbage with which it's unentangled, but it's very hard to prepare psi itself. Okay?
So isn't it the same as the existence of one-way functions?
Not really, no.
I thought usually the way you can compute but not uncompute.
Yeah. Well, there are related phenomena that happen with one-way functions, right? Like it is easy to map, for a one-way function, it is easy to map x comma 0 to x comma f of x.
Yeah, that's
right. It is hard to go from f of x to x.
That's right.
But I don't know that gives me an example of this.
I see.
I don't see, right.
Oh, because of the entanglement.
Yeah. I'm asking a different question here. Yeah. So I'm asking, is there any state that is easy to prepare, but only if you also prepare in tensor some garbage?
Is the answer that's no?
No, that's why I'm asking. That's why it's a question, yeah. I would love to have, even like modulo some cryptographic hypothesis or something, or, even just a candidate, just a plausible candidate for such a situation. I don't know whether it ever actually arises.
What do you
It's a
think?
very bizarre thing from the point of view of black holes.
Yeah, okay, I would say it would be a bizarre thing, period, but, but yeah, okay, but yes, but I can't rule it out. I know that this distinction can matter a lot. I don't know if it actually rears its head anywhere.
And classical
Yeah.
strings, following up on Daniel's
Yeah.
question, classical strings will not give you any example because
That's right.
complexity is just.
Yeah,
That's right. If G were just a classical string, then I would just, get rid of it. Yeah, I would just design my circuit to get rid of it. Yeah, so right, okay.
There's a baby version of this
Hmm.
where you're interested in certain kind of quantum ground states.
Mhm.
And it's easy to prepare, or you can prepare a certain state with a short depth circuit if you prepare that state plus something else.
Yes.
But if you prepare just that state by itself, it require a circuit
Yes,
that grows
yes.
linearly with system size.
Yes, good. This was explained to me that in the case of, I guess, spatially local constant depth circuits, that there are phenomenal.
But I thought in that case, that state T must be also complex.
No, like a quantum Hall state.
Yeah, so like T and psi are both similar.
Yeah, but the
Okay, all right, good. All right, so let me wrap up. Okay. All right. So. All right, good. So the last remark I was going to make was just that. So we have, if we're going to summarize the situation. So this was what the equivalence theorem said, that these two complexities are asymptotically equal, ignoring constant factors. These are both certainly, at most, the circuit complexity of preparing psi or phi themselves. Okay, and that in turn, by sort of a folklore observation, is at most the circuit complexity of V plus the circuit complexity of W, assuming V and W are orthogonal states. Okay, and for both of these inequalities here, I have examples where they are exponentially far from tight. Okay, so now what does, to wrap up, what does any of this mean? Okay, for one thing, it means that if we have a superposition of a state V with polynomial complexity and another state W with exponential complexity, then there is never any polynomial time experiment that you can perform that would measure the relative phase between V and W. Never. Right? So some of you might recall my and Lenny's earlier result, not yet quite written up, which said basically that if you have the generic or computationally universal Hamiltonian H, and you let it evolve for exponential time on a certain starting state, then you will generate a final state that has more than polynomial circuit complexity, unless some collapse of complexity classes happens, unless P space is contained in PP/poly. Right? So if you combine this equivalence theorem with my and Lenny's earlier result, then the corollary is that unless P space is contained in PP/poly, there can be no feasible experiment in general to measure the relative phase between a state and that same state after you have let it evolve for exponential time. Okay? Even if mapping one state to the other were merely thermodynamics hard, then still, measuring the relative phase in a superposition of the two would also be thermodynamics hard, right? And maybe that could help to justify this whole state-dependent observables business, or the separateness of the two branches and the many worlds interpretation, or things like that. Okay. For me, though, the equivalence between relative state complexity and relative phase estimation complexity also, has an interest that's independent of quantum gravity. Even for foundations of quantum mechanics. So if you think about it, what we're really saying is this. We're saying that in the Schrodinger's cat experiment, say, if you had the technological ability to detect that the cat was in a superposition at all, that is, to measure the relative phase between the alive state and the dead state, then you would also necessarily have the ability to bring a dead cat back to life. Right? To rotate it from the dead state to the live state. Okay, and so therefore, contrary to what pretty much every popularization of quantum mechanics has ever said, we need not call the ethical review board about the Schrodinger's cat experiment, right? If you can do it at all, then there is no permanent animal cruelty necessary. Okay, so maybe that's intuitively obvious, but I think it's still nice to have a proof. And Lenny's concept of relative circuit complexity as a distance metric between quantum states is the thing that lets you formalize that equivalence. Thank you.